Hi everyone, welcome once again to our Grade 10 Physical Sciences. Our focus today will be on atoms and compounds. Surely we had a well-deserved break. Welcome again to the second term. We shall be focusing today on the knowledge area, matter and materials, the last aspect of it, which is based on atoms and compounds, as I've indicated. Hopefully we are fresh and ready to go for the second term. Right. Let's get right on to it, people. As I've said, our focus is atoms and compounds. Right. Right. As you can see from the screen, matter is the core idea, rather the big idea. However, we must remind ourselves that matter consists of small indivisible particles, which are the building blocks. So this is the basic unit of matter, which is the atom. Right. Basic unit of matter, or the building blocks, if you may want to refer to it. So these are the building blocks of matter. These, at a microscopic level, we refer to them as atoms. Right. Now, these atoms, they make up what we call elements. So elements, as you would remember from the periodic table, these are individual substances that consist of atoms of the same kind. But these atoms of the same kind, particularly, have got the same atomic number as well as atomic mass. We're just trying to throw some bit of caution there, because remember, some atoms of the same element may differ in terms of the atomic mass. Remember the isotopes, which obviously come to mind. So elements is what you find in the periodic table, your hydrogen until calcium. You know, the first 20 elements that we've described. So these are elements, or they consist of atoms of the same kind. In other words, atoms make up elements, but these atoms must be of the same kind. Right. We also spoke about compounds in the first term. If you talk about compounds, remember compounds, they consist of atoms of different elements that consist of forces that join them together in a way that they make up substances which are a bit complex than atoms, because there is some bonding that is involved as far as compounds. So compounds are also pure substances, as you can remember. Compounds are also pure substances. Water is an example. Calcium chloride is an example. So these are pure substances. The same applies to elements. Elements are also pure substances, because we said they are not mixtures. In other words, they consist of atoms of the same kind, but these are atoms of different kinds. Different atoms that consist of forces that keep them together. So these consist of different atoms. Hence, we said atoms are building blocks of all matter. So in other words, elements are also made of atoms. Compounds are also made of atoms. Right. We also spoke about the chemical formula, which will be also our focus for today. In terms of chemical formula, remember, the names that we use to refer to specific substances are also very important, in the manner that we also go back to the periodic table and use symbols to write chemical formulae of different substances. Let's take, for example, water. We use H2O. So that's pretty much what we're talking about. Right. We're also going to talk about molecules today. Molecules are very key, because molecules can be of compounds. Molecules can be of compounds or elements. So we need also to pay careful attention to that, which will be one part of our discussion in today's session, of which, now that we spoke about compounds and molecules, elements of the same kind, or atoms of the same kind, can actually join together or be held together by forces, which forms giant structures. So this chemical bonding is very, very critical. And there are three types of bonding that we've spoken about. We've got covalent, right, which we shall also discuss briefly today. We also have ionic bonding. These are the different types of bonding. And also we have metallic So these are the three types of bonding that we shall discuss in detail today. Right, let's go straight to the core focus of the key concepts that will be very relevant as far as our lesson overview is concerned. Now, I want us to pay careful attention to the various aspects that I've mentioned for the purpose of today's lesson, so that at the end of the day, we achieve our set of objectives, atoms and compounds. That's the core focus of today's lesson. Right, moving on to the key concepts. Right, we shall talk about elements. Elements, we're saying these are pure substances. Right, remember, pure substances are those chemicals or substances that are not mixtures. Remember, in the first term, we spoke about heterogeneous, homogeneous mixtures. And in mixtures, there are no proportions, just maybe to bring that again so that we can draw a comparison between pure substances, mixtures. And remember, pure substances can either be elements or compounds. Elements which are made up of atoms of the same kind, as well as compounds which consist of different elements that are chemically joined together, which we spoke to bonding, which is also very important. Right. So these are pure substances. An element, a pure substance that can not be broken down into simpler form. Say, for example, we have calcium. Calcium consists of a specific type of atom which makes up this substance. In other words, it's not going to be scientifically or practical for us to break down calcium further without it losing its properties. We know that these atoms that make up these pure substances, which we refer to as elements, consist of these subatomic particles. But our focus is that as far as elements are concerned, they are made up of these atoms which are indivisible. If something cannot be broken down, sometimes we refer to it as indivisible. So this is another word, indivisible. This is another term for cannot be broken down, indivisible. Okay? In some sources, that's how they would refer to it into simpler form. So an example is calcium. We can take gold as an example. We can take silver. Any substance that we find in the periodic table can serve as a typical example of a pure substance, which we refer to as an element. Hence, we refer to it as the periodic table of elements. Right. Elements are made up of the same type of atom. Right. Now, the same type of atoms, let's be careful that sometimes we have atoms of the same element with different atomic mass as a result of different number of neutrons. We call these isotopes. Something just to bring to the fore so that the emphasis is that these atoms must be of the same kind, definitely not the isotopes. Right. Now, let's look at compounds. Compounds, these are groups of two or more, and they must be different, that are held together by strong forces. Now, if we talk strong forces, we also referred to the ionic bonding that you would have maybe dealt with to school as far as the first term part of matter and materials. So as far as these strong forces, we can talk about ionic bonding. Right? We can talk about ionic bonding. And remember, this one has nothing to do with metallic substances, because metallic substances, remember, they consist of atoms of the same kind. You take, for example, your transition metals. Right. Now, in this case, they are held together by strong forces or chemical bonds. These are molecules in terms of maybe covalent. We can talk covalent and ionic in this case. Right. Okay, so these atoms bond in specific ratios. Take, for example, H2O. Right. Water consists of two elements, that is hydrogen as well as oxygen. Right. Now, if you check hydrogen, in each molecule or unit of water, there are two hydrogen atoms and then one oxygen atoms. Hence, they react in the ratio 1:2. So as far as compounds are concerned, there is a fixed ratio in which these elements join together to form these pure substances. And another thing, again, that we need not forget, that compounds are also pure substances because they are not mixtures. Right. Compounds are pure substances. Very, very key for us to also include that. So having said that, I think it's very important for us to also realize the fact that what we have said as far as elements are concerned, elements, these atoms that of the same kind, rather, that make up these substances, they are indivisible. We cannot break them down into simpler form. We gave examples of calcium, hydrogen, gold, any element that you find in the periodic table is a perfect example of what an element is all about. And then as far as compounds, remember the fixed ratios in which these different atoms are combined with each other to form these pure substances. Right. Now, moving right along. Now, in terms of bonding, covalent bonds, these are formed when electrons are shared. The word core means to share, right? The word core means to share, if we can recall that. And then valent, if I can maybe make an emphasis on valent. Valent, it talks about the electrons that are found at the highest energy level, the ones that are actually involved in bonding. So these are high energy electrons, okay, at the highest energy level. Electrons at highest, okay, energy level, or which we refer to as the orbitals, right? So, in other words, core, it means sharing of electrons at the highest energy level. But these are particularly between atoms. It can be atoms of the same kind. So, in other words, we've got molecules, right? Molecules are formed as a result of covalent bonding. So, molecules can be molecules of elements, okay? They can be molecules of elements, okay, or molecules of what? Compounds. In other words, what we're saying is that when covalent bonding takes place, it can take place between atoms of the same kind, as well as atoms of different kind. But I must also indicate that we also have atoms of elements that which exist in monoatomic form. Take, for example, the group 8, which we refer to as the halogens. Those, they don't bond due to their stability. We remember that the group 8, which we refer to as the noble gases, right? What happens is that they are the only substances that exist as atoms. So we can't talk bonding, particularly with those substances. However, if we look at elements of the same kind, we can talk about oxygen or ozone. We obviously talk about the ozone depletion every day. It's a burning issue, which is quite relevant. Now, ozone is O3. Oxygen is O2. Now, if you check, a molecule of this element consists of atoms of the same kind, which are chemically joined together. So there are these forces that keep them together, if I may put it that way. Right. It can also be molecules due to covalent bonding of different elements. We've used water as an example. We can use carbon dioxide as an example. Now, if you check, the carbon is a different element to oxygen. And also, they react in a fixed ratio of 1:2. Hence, when covalent bonding takes place, it can occur between atoms of the same kind as well as atoms of different elements. Right. Now, it also says that these form between non-metals only. Now, let's draw attention back to the periodic table, which is, I'd want to think of it as our Bible. It gives us a guide as to exactly the trends, the atomic numbers. And if we talk about classification of elements, now let's talk about the first trend. We know that the group 1 and group 2 are your metals. Then you've got the transition block, which are still metals. And then as you go further to the right of the periodic table, we've got semi-metals as well as non-metals. Now, what are we saying? We're saying that covalent bonding takes place only between atoms of non-metals. If you check, carbon and oxygen are non-metals. Hydrogen is, yes, it's in group 1, but hydrogen is an exception. It's also a non-metal as well as oxygen. So it can only take place between non-metals only. These are the typical example. We've mentioned oxygen, ozone, hydrogen, sulfur, water, petrol, which we call, it's referred to as octane, which is an organic or a hydrocarbon, which we shall discuss later in the 12th grade. Right. So covalent bonding, that's as far as it goes. Right. The most important thing now is to take home is that as far as covalent bonding, it takes place between atoms of nonmetals, and these atoms are chemically joined together. They can be of the same kind, they can be of different kind, right? And what they form what is called the molecular structure, which we shall discuss after our short break. Now, let's take a short recess now, and we shall be back after the rebound. Cheers, guys. Hi, welcome back, guys. After a short break, we were just talking about the molecular structures as far as covalent bonding takes place between atoms of non-metallic elements. Right. The next part of covalent bonding that we shall look at is what we refer to as covalent network structures. These are network structures, as you may recall even from your biology that you did in the first term, your life sciences, we spoke about macromolecules. Right. Sometimes we refer to these covalent network structures as macromolecules. Right. They're called macromolecules. Okay. Right. Having said that, they consist of millions. Now, in terms of quantity, remember we said these are macro. Macro means large scale, big, huge, comparatively in size, if you want to think of it that way. Right. So they consist of millions. Still, it's non-metals because it has to do with covalent, which has to do with the sharing of electrons at the highest energy level. Right. So the atoms are bonded together by covalent bonds. So it means they overlap each other, these high energy orbitals, to form bonds. Right. It's a large and repetitive crystal. Sometimes we refer to them as the crystal structures or the network crystal structures, which consist of atoms that are bound together by strong covalent forces. So still, now, if you contrast this or compare it to the molecular structures that we discussed before the break, we agreed that as far as these molecular structures are concerned, it has to do with the bonding, which is the sharing. Now, remember, these can happen between atoms of the same kind, which we refer to as molecules of an element, or rather molecules of compounds. Now, let's go further and check. It says the structure have high strength. These are, I would want to think of them as the physical properties. Now, because they are giant structures or macromolecules, they are stronger compared to these, which are most often liquids, in gases, except for sugar, of course, it's solid at room temperatures. Now, they've got high boiling points, high density, which we discussed as the physical properties in the first term when you looked at physical properties of materials. So I'd want to think of these macromolecules as giant structures which are comparatively have got higher strength, boiling point, melting point. You'd even think of density as one physical property. That's to touch base with that. Now, let's look at the typical examples of these macromolecules. Right. Now, if you check, here we've got a structure. This represents diamond. Right. Diamond is a hard material, remember we said it's also used for cutting tools, because of its high strength relatively. So it is a very much useful everyday application. Now, because we said that they've got comparatively stronger, they've got higher strength, melting and boiling points, which are the physical properties. So this is it's made up of carbon. Now, these are atoms of the same kind. These are carbon atoms, which are chemically joined together, covalent. But they form a huge structure which we refer to as a macromolecule. Now, you'd want to think of carbon as a diamond, rather as an allotrope. If we talk about allotropes, I think that's another term which is very key. We're talking about substances which are made of the same type of element, but they differ in structure from one to the other. The other allotrope of carbon, if you can think of it, is this one that we have, which sometimes we refer to as graphite, the gray substance which is used even in the pencil lead, So this is a different structure to carbon because of the type of bonding is the same. However, the conditions under which these are formed, they differ one from the other. So these are what we call the giant structures or lattice structures. So carbon forms allotropes such as diamond as well as graphite. So this is a giant structure or lattice structure of a substance. So we call these network structures, covalent network structures. Covalent, why? Because of that which is the bonding. That's covalent bonding between the atoms of the same kind. Now, so this is a giant network structure of an element instead of a compound, because these are atoms of the same kind, right? So this is covalent bonding. Very key also to recognize that fact, right? And then examples of other network structures include diamond and graphite, as shown in the example that, and also silicon 4 oxide or silicon dioxide, which is also a giant structure, and some of boron compounds. Some of them, definitely not all of them, as you'd realize as we go further, right? Okay, so now we've spoke about the two different types of covalent structures, the molecular, which are comparatively smaller in size, and also we've spoke about the network structures, which are giant, which we refer to as macromolecules. Macro meaning big comparatively in terms of unit size. Right. Let's move along. Right. Now, the other key concept, which is also key because we're still talking about bonding, metallic substances, we want to be very careful as far as metallic is concerned, because this also has to do with between atoms of metals. So as we talk about metallic substances and metallic bonding, it has nothing to do with compounds, because these are atoms of the same kind. So the metallic bonding will particularly take place between atoms of the same kind, between atoms of the same kind, right? Of the same kind. So now this is particularly very prevalent with the transition metals, the block of metals in the center of the periodic table, which is very key. As I've said, we shall constantly refer to the periodic table because it kind of guides us as to what exactly is taking place. Now, in terms of classification, when we talk metallic bonding, it has to do with in most cases, it has to do with the transition metals. You take gold, silver, zinc, iron. These are the most common examples of metals in which metallic bonding takes place, and we shall refer to those as metallic substances because they are elements instead of what? Of compounds, due to the fact that it has to do with the same kind of atoms being bonded together. Now, so the atomic nuclei, is always positive due to the occurrence of the protons in the nucleus of the atom. Now, the electrons in the underlying shells are surrounding the positive metal ion, which we have said is because of the protons, and these are tightly packed together and organized as crystal structure, and the outermost orbitals overlap each other. Now, the overlapping each other is what brings about the bonding aspect of it as far as metallic bonding is concerned. That's the valence, which we refer to electrons at the highest energy level or high energy electrons. So valency are those high energy electrons. High energy electrons in terms of the orbitals. So these are high energy electrons which are delocalized. Delocalized, it means, I think in simple language, it would refer to electrons being displaced. They're not going to be confined around that nuclei of the atom. It means the adjacent nuclei between the adjacent nuclei, these delocalized electrons can actually move between them, creating that sense of element of that aspect of bonding, which we refer to as the metallic bonding, right? Now the smallest particle or the unit that makes up a metallic crystal, right, is what we call the positive metal ion core. So, or alternatively, we shall refer to it as an ion, right? The examples, like I said, copper, iron, zinc, and silver are your typical transition metals. These are the most common examples of substances that have got what we refer to as metallic bonding, right? Very, very important. Now, so metallic bonding would only take place between atoms of the same kind, particularly of the metal. I think after all has been said and done, that's what one needs to take home with in terms of metallic bonding. So the three types of bonding that we've looked at is the covalent. Is the covalent, which is divided into two, which is molecular, which forms molecular structures and network structures. Now, we've also looked at the metallic bonding. Right, let's move along and look at the next concept, which has to do with the types of formula. Right, in terms of ionic bonding, maybe before we look at formula, in terms of ionic bonding forms between metals and non-metallic atoms. In other words, ionic bonding will take place between two atoms of different kinds, in the sense that compounds would rather be formed instead of elements. Right. So, as far as formula is concerned, we use there's what we refer to as molecular formula. I'm going to refer to use water as an example. H2O is the molecular formula that would use to represent the substance water. Right. Now, this type of formula is the actual number. In other words, it says in a unit of, or in a molecule of water, there are two atoms of hydrogen bonded to one oxygen atom per molecule. Now, then it means if we have a substance like water, would have these chemically joined together, then they will also have their own forces between other. But now our focus for now is rather what the fact that the actual number of atoms of each element in this compound is 2 for hydrogen and 1 for oxygen. So the individual atoms, in this case, we've got 1 atom for hydrogen, right? Which is is 2 atoms for hydrogen, right? And 1 atom for oxygen. So this would be our typical what you call a molecular formula. This is the type of formula that we use to identify the substance. And then we talk about the empirical formula. So the empirical formula shows the simplest whole number ratio. In other words, for water, it's still we can't further simplify the ratio 2:1 in terms of hydrogen to oxygen. Let's look at another substance with the same composition, which is also a pure substance and a compound. Let's take hydrogen peroxide. Hydrogen peroxide is H2O2. Right. Now, if you think of it, it contains 2 atoms of hydrogen, 2 atoms of oxygen per molecule, which is the actual number, which is the molecular formula, okay, of this substance. Right. Now, and then if we want to go to the empirical formula, it means we can simplify this into a simplest ratio we can get. In other words, it would be 1:1. In other words, 1:1. 1:1, because for every 2 hydrogen, we've got 2 oxygen. So in other words, the empirical formula would be HO, which means 1:1. Now, in this case, the molecular formula of hydrogen peroxide is different from the empirical formula. Whereas in water, the molecular formula is H2O. It means if we can't simplify this further, it means the same molecular formula will also be empirical formula for hydrogen, for water. So we need to also be careful. And then in this case, this will be a different empirical formula to the molecular formula of the same substances. So the smallest repeating unit in this case is HO, right? Okay, right. Now, having said that, I think it's very important for us to also realize that these types of formulae, they vary. And maybe in some of the schools, we have the privilege of having the models that we use to present. We also have another type of formula, which is referred to as the structural formula. We can use the ball and sticks model, to play around and construct different models of substances, just to show how atoms, whether of the same or different elements, join together to form molecules. So in terms of structural formula, what would be key, I think, would be showing the actual actual bonds and the actual atoms, how they join together to form a unit or a molecule of a particular substance. Right. For now, I think we've discussed quite a lot. I think we need to take a short break. Then after that, we shall look at the feedback, the activities that I'll give you time to attempt. And then after that, we could maybe do feedback and consolidate. Let's just go and take a short break, and we shall be back after the rebound. Thanks. Hi guys, and welcome back again. Remember, now is the question and answer segment, where I shall expose you to a different types of questions, and then I'll give you also time to attempt that, and then we do our feedback as a collective. Right, now let's get right on to the questions. Name the three types of chemical bonds, okay? And then again, which two types of covalent bonds, two types of covalent molecules exist. Give examples in each case. Right, I'll give you 3 minutes for that to try and respond to those two. Then quickly we shall do our feedback. Let's go for it, guys. Okay, guys, welcome back. Hopefully, you've made your attempt on the two questions based on the three types of chemical bond. Right, just to get right on to it, we know that we've got covalent bonding, right? We've got covalent bonding. Also, we've got ionic bonding is another type, ionic bonding. And we also have metallic, right? We also have metallic bonding. Right. Now, we know that the covalent bonding consists of atoms. They can either be, they form molecules molecules. These molecules can be molecules of elements or molecules of compounds. Take, for example, oxygen. We say it is an example of a molecular substance in which atoms of the same kind are joined together. We also have carbon dioxide as another example of a molecule of a compound. And now, typically, we say these occur between atoms or elements which are non-metals, right? So this happens with what? Non-metals, between atoms of non-metals, right? Very key to remember that. And then as far as ionic bonding, we have metals combining with non-metals, right? Metals combining with non-metals. Now, what would happen? Primarily, the metals will form what we call the cations through the transfer of electrons. So what happens if they form cations? It simply means that electrons have been lost, and then the non-metals they will also form what we call N-ions, which gain electrons. So these are ionic crystal structures. They form what we refer to as salts most often. Take, for example, sodium chloride as an example, right? Now, and then in metallic bonding, this occurs between atoms of metals, which are typically the transition metals. We know the sea of delocalized electrons and the positive nuclei, which happens to form due to the delocalized electrons moving between adjacent nuclei of atoms to form very strong bonds. And that's why we say these metals have got very comparatively strong, higher strength in terms of the physical properties, melting point, density, as well as the boiling point. Then the two types of covalent molecules that we discussed today are the molecular structures, right? Molecular structures. Right, molecular structures are covalent. They are covalent, most definitely. Molecular structures are examples of such structures is, let's say, carbon dioxide. If you talk of carbon dioxide, carbon, when it bonds with the oxygen, if I may use that as an example, that's typically what happens. Now, this is a molecular structure due to shared valence electrons. Now, also, it can happen to form what we call macromolecules or network structures, such as diamond and graphite, network structures. This is another type of bonding which forms the macromolecules that we discussed, right? These are macromolecules. Okay. Now, the typical examples of these is graphite. We mentioned graphite. We also spoke about diamond, and also silicon dioxide or silicon 4 oxide, which is typical in sand, glass, and quartz. These are some of the most common materials that are used in everyday life, right? So these are the typical examples. If we can maybe look at the next section of a set of questions, it has to do with also classification. It says here, copy and complete the table on each of the following substances indicated. Now, the emphasis is the name of substance given in words. So you'd identify the type of bond. Remember the three types that we spoke about, and then also the formula of the substances. Some of these can be elements, some can be compounds. Right. I'll give you say 3 minutes to do that. Then we shall do the feedback together. Right. Let's go for it, guys. Okay, guys, welcome back again. Surely we've made our attempt on the table in terms of completing the type of bond as well as coming up with the formula of each of the substances that was given based on today's session. Now, let's quickly go right through it. With the first substance is hydrogen bromide. I want you to be very careful. Bromide. It consists of hydrogen and bromine, right? Hydrogen and bromine. Right. Now, and it's bromine, but the name at the end is, if it's a halogen, it will end with the Di instead of an Ne. Now, remember, between hydrogen and bromine, there is sharing of valence electrons. Now, the type of bond in this case will be a covalent because of the sharing. So this is a molecular substance, if you can think of it, right? Hence the formula, because there is one atom of bromine and one atom of hydrogen in a unit of these substances. Hence the formula will be HBr, right? Carbon dioxide, which is something that we have looked into. The di suggests that there are two oxygens. It consists of carbon and oxygen chemically joined together, but there are two oxygen. Remember, the sharing of electrons, valence electrons. In this case, the double bond, as we shall discuss later when we do the bonding. So the sharing part, which means this is also another covalent molecular structure, right? Covalent molecular structure. Carbon and then dioxide, that's the CO2. Then gold, the type of bonding. Gold is a transition metal, right? Remember, this is a transition metal in that special block in the periodic table. So because it's a metal and it consists of atoms of the same kind. Now, these is a typical example of what we call metallic bonding. Because we discussed it as an example. So this is a metallic substance or a metallic element. So we just write down the formula unit as Au there, which represents the atom of that element, which is the basic unit of the metal. Right. And then potassium chloride. It consists of potassium as well as chlorine. Now, potassium is a metal and chlorine is a non-metal. So in this case, there is actually the transfer of electrons taking place between these two substances, with the potassium forming the cation and the chlorine forming an anion. Hence, this is then the strong forces, or which we call electrostatic forces, join these two ions. So these are electrostatic forces, or sometimes we refer to them as Coulombic forces, right? Coulombic forces, but the type of bond involved in this case is indeed ionic. So the response that we're looking for is ionic, but remember, ionic consists of electrostatic forces between the cation and the anion, between a metal and a non-metal. So there's one potassium. We always start with the positive one, followed by the negative in one chlorine atom. So for that reason, it gives us that. Okay, let's look at the last set of questions, which is also in the form of a table. Right, in this case, we've got elements present. We want the type of compound and the formula. I think we get the type, the sense of what we want here. So this is the elements in terms of the composition. It can be a single element, it can be two or different. If it says and, it means they are generally chemically joined together. So it would not necessarily be a compound. It would be, let's say, a substance, just to generalize that. Right. Okay, I'll give you 2 minutes for that, and then we will do the feedback and wrap it up. Let's go for it, guys. Hi again, guys. Welcome back. After our short attempt to this very last program, last question in our question and answer session, let's look at the feedback together. Now, the elements present in this case is magnesium and oxygen. Right. You remember magnesium is a metal, and then oxygen is a non-metal. And obviously, there shall be a transfer of electrons involved. In this case, this is an ionic substance or ionic compound because of the transfer of electrons. Right. Hence, the formula, because magnesium is in group 2, oxygen is in it forms a magnesium 2 plus ion. So for that reason, we get the formula MgO. Right. Then for hydrogen and oxygen, depending on the number, if it was 2 hydrogen and the oxygen in terms of composition, we can immediately think, say, of water, as a substance. We can think of water. Now, water has to do with the sharing of electrons or valence electrons between hydrogen and oxygen, which means in this case, it will give us a covalent molecular compound. So this is a molecular substance. In other words, in this case, it's a compound again. So it will be H2O, right? And then magnesium and chlorine, it has to do again with the transfer. It means once we mention transfer, it takes us to ionic between a metal and a non-metal. So in other words, we've got MgCl2, which is very important. We shall discuss how we come about with the two there in terms of chemical bonding, which is the next lesson that I anticipate. Now, if you look at the copper atoms, this is an element, hence we refer to this as a substance, and this is a transition metal. So indeed, this is a metallic substance. Is a metallic substance. So you just write the unit there, which is the atom, or the formula unit, which is the atom of copper. Then carbon forms what we refer to as the giant molecular, network structure. This is a covalent molecular, network structure. This is a network structure or a giant structure. It can be, let's say, for example, which is covalent again, a network covalent. But this one is a giant structure, which you can think of, they say carbon in the form of graphite, graphite, it's just C, it could be carbon, it could be diamond, just to mention, remember the allotropes that we discussed. So this is basically, these are covalent at the end of the day, which forms a network or a giant structure, like I've said earlier on. Right. Now, this brings us to the end of today's session. There are quite a lot of things that we discussed, but what is it that we take home, as far as chemical bonding and in terms of compounds and atoms of elements? There are three very critical ones. We mentioned covalent, molecular, we also dealt with network structures, which are lattice structures, the giant, which is a molecule. We also spoke about ionic compounds, between metals and non-metals. We also spoke about metallic. So these are the key aspects that we dealt with today. Hopefully this was an interesting session from myself, Temba Ngube. I think we shall meet again in the next section. It's cheers and bye-bye for now.